approach. So before going into the paper, I'd like to start with by just showing some results and kind of getting an intuition of what they're actually trying to do. So what they want to do over here is they want to do some on-the-fly control with natural language. For example, in this image, you can see the input is just a red car, and then they give in text input such as the different actions, which could be the red car moves, and then an explosion happens, and then the red car continues to move, and so on. Sorry for stopping you, but your screen is not being shared on the live stream. Oh, okay. Is it good now? Is it good now? Yeah, so as I was saying, they aim to do on-the-fly control with natural language. You can see some examples over here, where given an input image and certain actions in some time, it aims to generate a full video and a full visual content around the particular actions. And you can see that it works in a lot of different domains. We can see outdoor scenes, indoor scenes, even humans. It can do multi-view and as well as some animated games as well. Um, and this could also be used to like predict different futures where given an initial state, we could try to see what happens if we put the red apple and what happens if we do something else. So this kind of thing could be used as well for making decisions while driving or certain robotics applications. And you can see a lot of more examples here as well. And something that they really try to do over here is kind of getting into all the different domains at once. And some issues you might observe here are, for example, for this particular one, you can see that it's an apple, but once it goes into the box, it kind of becomes an potato. So there are some issues still which would be nice to be addressed. And for the human images as well, you might have noticed that the blinking seems to be quite a big problem. The blinks are not at all natural and might seem really weird. Um, Right. So now let's get into the paper itself. So first, I like to start with talking a bit about what world models are. So world models are basically models that, given a particular state, such as an image and a particular action, they aim to predict the next state or kind of predicting the future as to what would happen next. And before this paper, most of the works generally did this kind of stuff only for particular domains such as robotics or maybe driving applications. Some of them include one such as this one. This is a paper by Google Brain, where they use reinforcement learning to kind of simulate open AI gym environments. So these are basically like 2D games, and they use a sort of reinforcement learning based architecture. And you can actually go to their website, and this is one of the simulations over here. So there are like orange balls coming towards us, and we are supposed to move left and right. So right now what you're seeing is the reinforcement learning model playing itself. And under the hood, how this does is that it kind of simulates both the left and right directions and predicts what is going to happen, and it uses that knowledge to make decisions as to where it wants to move. Some more work in this field includes work such as Transdreamer, where they combine reinforcement learning along with some transformer-based architectures to do this problem. Um, then we also have another paper by the MIT lab, where for the first time, they combine uh, text and task-based models along with visual models as well as action models. And the architecture looks something like this, where given a particular task, they use the LLM to kind of break it into different tasks. And then given certain images, they plan to make an entire plan for how to execute that particular task. So this is mostly applicable in like robotics based applications, where given a task and initial state, it would predict the particular pattern to follow to complete a given task. But as you might see that this kind of application is works well only for tasks and not exactly other kind of stuff. For example, the one which you saw here where a mountain and the scene goes dark or something like that. So this is not exactly a task, and it's not something that this architecture would be able to plan and solve. Another recent work is driving into the future, where they use similar world models, diffusion-based architectures to kind of make driving decisions, where it kind of tries to imagine all the different possibilities while driving, and then it kind of uses a reward and decision-based model to decide which option it wants to choose. But once again, this type of model would be applicable only to driving scenarios and not really a broad scenario. And lastly, a very recent work we have is Genie by Google DeepMind. Where given a particular image as prompt, it could be either a AI generated image, a hand-drawn image, or even a real-world photo. It aims to develop 2D world and 2D interactive environments for that. So, for example, if you look at this image, it basically contains like wooden planks and a man over there. After generating it would make it into a sort of 2D game where you could actually control the man and jump over stuff and move to the left and right. And all of this is like generated on the fly. And their architecture looks something like this, where given some T frames of the input, they tokenize it using the video tokenizer, and then they use a latent action model to kind of infer what the actions made between different frames were. And both these tokens are then passed into the dynamics model, which understands more about the movement and stuff and kind of predicts the next frame. Uh, but once again, like this could be used only for 2D gaming environments. And though it does model real world images as well, it would only be able to model them up to a particular aspect where you try to move something or try to jump over something, not really in a general way. Um, this is what the paper Pandora aims to solve. And some of the major issues with previous work in this field have been that the models particularly try to work only in some particular domains, such as either cars or either games or something like that. But this model tries to do like everything from planning tasks to driving, even scenic beauty and stuff like that. Um, and it is also one of the first ones to actually do free text actions where you can literally say anything like the car moves, car goes backward or something. And it will try to interpret that natural language and try to do it as close as possible. Um, and the another issue with using diffusion-based video generators is that most of the times they only generate video of a certain length, let's say 2 seconds or something like that. But this method, what it does is it uses an autoregressive approach to kind of make the video longer, and they claim that they can make videos of up to 8 to 12 seconds. Yep. Autoregressive basically means that you assume that the latest state is actually the first state, and you try to recursively infer from that. Uh, so yeah, let's get into the architecture. So given this initial state S1, which is actually an image and a particular action, which let's say the red car moves along the path, it passes the image through a vision encoder and an adapter pair, and it generates some tokens for it, which basically encodes this entire information, all the information about this particular image in the form of tokens. And then we also tokenize the text instructions. And then we also have the third input to the LLM, which is a query embed. This is basically something which prompts the LLM to kind of generate the video. So this is mostly a task-based query. And once it goes into a pre-trained query comes from the prompt itself. Um, Query doesn't come from the prompt, but it basically like gives the command to generate a video in a way, intuitively.
So like what? So like in like inference, I guess like what information does it have? Or what?
Um, in inference, it's actually a learnable parameter.
Oh, I see.
Yeah. Um, Yeah, so moving a step back, actually, so over here they make use of pre-trained LLMs as well as pre-trained video generators. Now, pre-trained LLMs are basically like anything like GPT or something, which takes in text input and gives out text input. Um, and in this case, they make use of the Vicuna model, but in reality it could be any other thing such as GPT or something. And for the video generator they make use of dynamic crafter, which is a diffusion based video generation model, which given a video and a text input modifies the video in some way. This could also be replaced by anything else such as Sora or something. um, so the main application over here is that they make use of pre-trained larger models, and what they do is basically make this entire framework around it, which utilizes these to the best of its capabilities to generate a world model sort of approach here. Um, right. So given the visual information from these tokens, and the task information from these tokens, as well as a query embedding which prompts it to generate videos, it goes into the LLM and it's processed over there to again give out some final tokens, and these are again passed through an adapter and goes into the video generator. And the video generator then takes in some initial frames and generates the next video. So with the video generator in this case generates 16 frames. So over here you would expect a video which has 16 frames. And then this process continues again in a recursive approach where S2 goes into another encoder, adapter pair, task, query, and it again comes out, goes into another video generator. And in this case, now last four of the frames are taken into account and the next video is generated. So it goes on in this auto-regressive approach. Um, Now, some of the issues with training this model is basically a lack of data, as well as being able to make the entire thing. Since they use many different models, they want to make the entire thing work together as well as make some controllable and consistent videos. So to do that, they divide the training into two stages, which is the pre-training stage as well as the instruction tuning stage. So in the pre-training stage, um, the most of the pre-training is already done in the form of the pre-trained large language models as well as the pre-trained video generators. The other things which we are left to pre-train are these adapters and encoders over here. So to train those, they make use of a WonderCam dataset, which has a lot of video and text pairs. So they pass in. So in under the hood, these video generators and LLMs, their architecture basically looks something like this. Um, this is the dynamic rafter model. Um, so under the hood, it kind of looks something like this, where given the video or image and some text input, it again goes through an encoder and then it goes on to its own architecture. So instead of passing in videos and using this encoder, in the paper, we actually want to skip this step where we instead directly pass in the encoded values and instead of passing in videos. So to do that, we actually use these adapters and encoders, our own adapters and encoders. Um, so we need to train these. To train these, what we do is we pass in a video text pair as input over here and compare the encodings generated over here with the encodings generated by the original model after this step, which is over here. And we run an L2 norm loss across both these encodings. And so that this is the first stage of training for adapters and encoders. Um, then in the next step, we have the instruction-based fine-tuning. For the instruction-based fine-tuning, um, the basic the main idea here is we want to make it real-time controllable. So in our data, we want such that for almost every frame, we have a different text information, but such kind of data sets are really scarce. So they make use of some YouTube videos as well as some other data sets, and then they prompt GPT-4 Turbo on it to create captions for each frame of the videos. And finally, with that, they end up with about 500K video text pairs from the YouTube videos. And after combining some more data sets, finally they end up with almost 1.2 million video text pairs. And you can see from the data itself that the categories are really broad. So they have YouTube videos, they have indoor, outdoor, robot videos, driving videos, as well as game videos. So this really,
So you mentioned that first you pre-train the model and then you fine-tune them.
right.
Can you explain the benefits of pre-training the model and then fine-tuning on it on a particular data set?
So the reason why we pre-train the model and then fine-tune is because in the pre-training stage itself, it would be actually quite difficult to learn too many instruction-based methods along with the consistency method. So in the pre-train method, in the pre-training, we mostly focus on generating consistent videos. And then in the second stage, which is the instruction-based fine-tuning, we try to make the model understand how it needs to adapt to different instructions. Um, yeah, so after doing this, finally we end up with a data set of about 1.2 million video text pairs, um, which are then used to train the architecture once again. And since we have now video text pairs, we can do an entire round of training once again, fine tuning on it. And now the model should be able to understand the instructions as well as generate consistent and large domain videos and applications.
Obviously, like what does the captions for each of the frame in the data look like? Are they like clip captions? Can you just like watch the video of the clip and then make captions and then train on that, for example?
Probably you could do that, but over here they make use of GPT-4 Turbo to do that,
Or to like,
to caption the videos. Yes.
oh, I see.
They don't really give examples of what that looks like, but probably like it might write like a paragraph about the video or something, I guess. Um, then for the results part, they don't really have any interesting evaluations yet. They just present some of the videos the same as the ones on the website, um, which we already saw. But some limitations which we notice over here are uh, particularly for these cases, um, where you can see over here that uh, the action says that the train door should open, and the door does open, but also the first half of the train vanishes. So that's an issue with some complex cases. As well as over here, it says to take out the nozzle, but it doesn't, and it just does something else.
So, is the initial frame the image or is the initial frame like, yeah, so
Yeah.
is the input like the image or do you give like a video? I thought it was a video.
Initial input is an image, yes. The image on the left is the input over here, this one. This image. Yeah.
I guess this is happening because of lack of training data.
Yeah, it could probably happen because of a lack of training data, as well as like it said that the train door should open. Now, I guess like the LLM interpreted open to be something like, I don't know, open the train, I guess. So it just open something.
The split open.
Yeah. Over here as well, it's said to take out the nozzle. It took out something, but that's not the nozzle.
Yes.
So it does have little bit and some understanding, but it still fails in some complex cases such as these ones.
So do you think this could work for like novel views? If you say like, how does this thing look when rotated or something like that?
Yeah, you can actually see a lot of those examples here as well. Over here actually. Yeah. So for example, this is one of the training data sets, training data where this is the input image and this is the video generated where it says look down 30 degrees, turn right, look up and stuff. And something similar generated on a test data would look something like this, where it is actually able to infer outside the bounds as well. And this is something for real world cases as well. uh, where it given only this as the input image, it is able to generate like an entire environment and an entire game around it.
Oh, oh. If you go like to the down one,
Hmm.
if you, I guess like if you just see this, the geometric consistency seems really off.
Yeah,
I mean, this isn't a possible video
that's true. Yes.
because after in the third state, the
Mm.
left wall dimensions are incorrect. You could never have like that view, right? So it doesn't understand maybe like geometric consistency, I guess.
Yeah, there are definitely some issues with geometric consistency as well as some physics-based motion stuff as well. It kind of misses it sometimes.
Still, it's looking really promising.
Yeah, it is decent, yes. Like another thing would be like, for example, over here it asks, this is a really simple case which should be like pretty straightforward. But when it asks to pick up the wallet, it just does like something completely weird in this case. So most of this could be attributed to the lack of training data itself, and also since we trained it on Chat GPT, like GPT-4 generated captions, they themselves might be noisy sometimes. So that could be one of the main reasons why this happens. So it would be really interesting to see how it would perform with some good, better data and well captioned videos as well. Um, And then, like we discussed before, the video generators and pre-trained LLMs themselves are just off-the-shelf models, which means that they just make use of any other pre-trained one. So these could be easily changed as well. And it would be really interesting to see what happens if we use something like GPT-4 here and something like Sora over here, because the video generated by Sora are generally like much more capable than Dynamic Rafter. In fact, like I have some of the videos from Sora here as well. Uh, you could look at that. So these are some videos generated by Sora, and it also works on similar principles where, given an image, it first uses a visual encoder and then generates the video. So this is where we would need to break apart the model similarly, and instead of using their encoder, we would use our own encoder through the LLM and adapters. And you can see that the videos generated here are of a much higher quality as well as a lot more geometric and spatial understanding. Um, though they themselves as well, they do similar tasks as well. I think over here where they have a video to video editing, where given an input video and some text information such as keep the window, make it winter or something. It does do those changes as well, but uh, one of the limitations here would be maybe it's not auto-regressive, so it might be of a certain length. It might be able to make videos of only a certain length. Um, Hopefully, I think if Sora they themselves try to do some techniques to make their videos longer, I think this itself should be able to beat Pandora itself, because these videos are of much higher quality. Though they themselves as well have some flaws, such as this one where they themselves struggle in understanding some physics where like breaking glass and stuff like that is really weird. So there is definitely some room for improvement and would be interesting to see if we can have some more physics-based information in these models, some more material-based information in these models. Uh, I guess they would be able to perform better.
Yeah, not example of glass breaking. I think it is a case of the model just having enough information how the glass behave in general.
Right. Yeah, are there any other questions from anyone?
How large are these models? In terms of the training complexity,
In terms of what side?
training complexity, like
Training time for like these LLMs and video generators probably like months, I guess. But for this one itself, they don't really release the time. But since like most of the larger stuff is pre-trained already, I don't think it would be anywhere of that type of order. And also like they have like really less data. They have just 1.2 million video text pairs. So uh, I don't think it would take too long.
how large, how large, like, in terms of the parameters,
Um, in the LLMs, like
the entire update.
um, I'm not sure how large exactly it would be. Yeah, and even
Like, so, so, yeah.
hmm. Yeah, they haven't really released their training times and stuff like that yet. But I'm guessing I'm guessing it would take quite a bit of time, but not like months or something. Probably a couple of days should be enough.
So not just this, like, the other were not, architectures, like how large are they? Uh, Like the other tables that you showed.
Right. Um, how large are they? I don't know. Let's see. Um, let's see if they give some information about how large they are. Yeah, so they have like 2.3 billion parameters for this one. 2.5, yes. Yeah, so this is also probably about similar size, if not more. You had a question? No? Okay. Yeah, I guess we finished a bit early, so uh, feel free to hang out and have some pizza. Um, and if you have any questions or want to discuss anything, you can feel free to do that as well.
But these models are available for anyone to use.
Yes, they are, yes. Like if you go to their blog page, um, they do have a GitHub
Okay.
where you can
They
use,
have plugins.
yes. So they have all the code and they also release the model and inference code. So should be open to use this one. Yeah, just lastly, thanks for attending the paper discussion. You can feel free to follow us on social media, and we plan to host weekly events during the summer. So if you yourself have any recommendations for which papers you want to be discussed or uh, what particular events, any other events you would like for us to run, feel free to join our Discord and you can write us there or our email, talk to us in person. Um, there's like pizza and cakes there. If you have some specific food requirements or some other food you would want to see in future events, feel free to talk to us about that as well. Great, thanks.